Okay, we are talking about different components of the traffic system, and there are 5 of them. The first one is a road user, and then we have the vehicles, the roads and streets, traffic control devices, and the general environment. We talked about the road users, mainly 2 of them, the characteristics of the drivers and the pedestrians. Then we started talking about the vehicles, okay, and for vehicles we have 4 important characteristics for the design of the highways, okay, and these characteristics include the deceleration, acceleration, and turning, and the turning can be seen for low speed and for high speed, okay. If you are considering low speed turn, then the only thing we need to consider is the size of the vehicle, okay, and the reason is the forces which are acting on the vehicle. So there are less force acting on the vehicle when it is making a turn on with a low speed, okay. So if you just consider the space required according to the size of the vehicle, that's enough. But when you have high speed turns, then you need to consider the other forces acting on the vehicle as well, and today we are going to start with this concept. So when the vehicle has not started turning, it is going straight, right? Okay. So whenever you have a turn or whenever you have a curve, there are 2 forces which start acting on the object, right? When the object is going around in a curve, there are 2 forces which start acting on the object or the vehicle in this case. Which are those 2 forces? Huh? Any object. Don't think about the car. Any object which is rotating, there are 2 forces acting on the object. What are those?
Centrifugal.
Huh?
Centrifugal.
Centrifugal and you miss the one which is written. Centrifugal and am I the only one who is seeing this? Centrifugal and come on, for God's sake. Like, I didn't ask you which one is which, because that I don't remember myself. Centrifugal and centrifugal, right? Is written there or not? I just want to confirm. Written, right? Centripetal and centrifugal force. Okay. So the vehicle is trying, or the vehicle is moving straight, and then there's a curve. The vehicle has to make the turn. It has to go around the curve. The inertia of the vehicle, the initial motion of the vehicle, is away from the center, right? It is, the vehicle is initially going straight. Okay. So now you have to force it towards the curve, right? You have to force it towards the curve. So the vehicle has initially centripetal force acting on it because it's already away from the curve, right? Okay. The force which is away from the curve is the centripetal force. So this is already acting on the vehicle. The vehicle is already in a motion which is straight motion. Okay. So it's already going away from the curve. Now you have to force it towards the curve. To balance the centripetal force, the motion of the vehicle, the straight motion of the vehicle, then we take the help of 2 other forces which are, or 2 other elements, not forces, which are super elevation and side friction. Now what is super elevation?
The
What is this?
inclination of the road toward the center of the radius.
I'm sorry.
The inclination of the road toward the center of the radius.
Yes. See. Okay. It will make your life much easier if they allow to, take pictures of your hands and mouth and so on and put in the exam paper, right?
I will do it.
Okay. So it's the inclination of the road. So inclination is towards what? Towards the center. Okay. So it is pushing the vehicle towards the center by means of the slope. Okay. So that is super elevation. And side friction means friction between what? Tire and the road. Okay. And why we call it side friction? Because now your tires are doing what? They are turning. Okay. So in the turning situation, then we have the friction which is sideways as well. So this is, we call it side friction because it's in the transverse direction, the direction in which you are turning. Okay. So these 2 factors help the vehicle to make the turn safely on high speed. Okay. Now you see we have what here? E and F, right? So these are the two elements which are trying to balance the centripetal force. Okay, this is the effect of the centripetal force, which is dependent upon the weight of the vehicle, the speed of the vehicle, and how much space you are giving the vehicle, okay, to make the turn. So these two things should be balanced. To make the turn safely, these two should be balanced. The road elements as well as the centripetal force or the effect of the motion of the vehicle. They should be balanced. If they are not balanced, then the turn will not happen, and in that case, there is a chance, because it's high speed turn, so there is a chance that the vehicle may flip, it may go over the lane, it may hit other vehicles or the side of the road, it may overturn. So all these possibilities are there. Okay, when in the first case, when the vehicle was making the turn at low speed, all these cases are not applicable because the speed is very, very low. The vehicle is almost stopped. Okay, remember the limit was less than 10 miles per hour. Okay, so less than 10 miles per hour speed is very, very low. At that speed, there is a very rare chance that the vehicle can overturn or hit, okay, or hit something very badly. So now if you look at this thing, super elevation is what? Huh? No, it is what?
Inclination.
Inclination, right? So it's a slope. Okay, so slope will be in some percentage, right? Some friction value, point something something. And F is coefficient of side friction, which is also a fractional value. So if you multiply two decimal values, what happens to them? The answer is even smaller. Okay, so E into F will be a very, very small number, and you can neglect. Okay, so this is gone. Okay, now I'm designing a curve. So I'm looking for which value? R. Okay, which is what? Radius of the curve. So I will take radius on one side, everything else on the other side. Okay, so this is the equation with the radius. Okay, so what do we have here? Yes, so we cancel out this term. Now we have 15 here. Okay, 15 is because of, first of all, the G value. G is what? Huh? Gravity. Okay, G is gravity. Okay, so gravity is what? 15? No? No, right?
No.
Okay, so what else happened here? So I put the value of gravity because I know. Okay, what else happened? Times R. R is there. What else happened? How did I get 15 here? What else I did to this equation? What is this? In feet. Okay, so I need to convert what now? Which thing I converted to feet? In all this equation, which is required to be converted?
Speed.
Gravity.
Speed.
Speed. But gravity we know the value, right? We need to convert the speed. Speed is varying, right? Gravity we know the value. The value is constant, right? I don't need to convert it. I know the value. Okay, so speed. Speed is in miles per hour. Okay, so you put the and it is what?
Square.
Square. Okay, so this this 15 is the gravity divided by the square of the conversion. Clear? Okay, the value of gravity divided by the square of the conversion. So I got 15 here and I got 125 here. This is when the speed is in miles per hour. So the conversion factor of miles per hour to feet per second. And the gravity was obviously in feet per square seconds. Okay, and then you got the answer in feet. This is when the speed is in kilometers per hour. Okay, so then the gravity was in kilometers, meter per square seconds, and the conversion was from kilometer per hour to meter per second. Okay, so this means what? Huh? Okay. How do I get 15 here? There was G here, right? G is the constant. Okay, and I have a speed in miles per hour. So I'll take the value of G divided by the conversion factor of speed. Okay. From miles per hour to feet per second. Anybody knows the factor? No. Anyone else? 1.47. Okay. But you have to do the square as well. Okay, so the value of gravity divided by the square of the conversion factor will give you 15 here. Okay, but that is in miles per hour to feet per second. Here, I want the radius in meters, so the speed will be in kilometers per hour. Okay, and gravity will be 9 point something. Okay, so this 125 is gravity divided by the square of the conversion factor from kilometers per hour to meter per second. Okay, which is 0.2 something. Clear? Okay, we have already done these things in the highway course as well. Okay, yeah, so E and F super elevation, we have a range here. Okay, you can pick values from this range and you can check if they are safe for your highway or not, but you should not exceed this range. So the minimum value of super elevation is 0.5%, okay, which means that the car, or there is no issue of safety there. Okay, so 0.5% is given for what purpose then? Drainage, okay, which is normal. Okay, any road surface will have some slope for drainage. This is very, very nominal. If you have very high speed, then you may go up to 12%. Okay, but you should not exceed this value, because if you try to exceed this value, then there is a chance that the vehicle may slide over the surface. Okay, so more than 12% is not recommended for normal surfaces. Okay, if you have road surfaces which are covered with water or snow for most of the year, then you should further limit it to only 8%, because on wet surfaces there is a higher chance of sliding, right?
Yes.
So we further reduce the slope to avoid this chance. Okay, so 12% is maximum for normal surfaces and 8% is normal for snow or water covered surfaces. Clear? But it doesn't have to be 8% to 12% in every case. This is maximum. These values are maximum. Okay, then the F value, side friction can be measured in the lab. Okay, you can measure side friction in the lab, or there are some experiments you can do on the road as well to measure the side friction. Okay, there are equipments available. One of them is called the pendulum equipment, in which you can put a piece of the tire with the equipment. You can go to the road, it can give you the value of side friction. Okay, and these values should be adopted for wet conditions. Okay, because again wet conditions means the pavement will be slippery. You will have more chances of going out of control and problems with braking and turning and so on. So we consider the worst case. Okay, and they did this according to their research. These are the values of side friction they have got, and this is depending upon their speed. Okay, and you can see when the speed reduces, the speed increases, the factor decreases. Okay, you have less friction or less side friction available, then you increase what? Speed is already increasing. I have to balance it now, so we have to now increase super elevation. Okay, this is how these two factors can be used. Okay, so high speed, obviously I cannot control side friction. This is something which is happening naturally between the tire and the roads. Okay, but super elevation is a design, part of design. I can control it in addition to radius as well. Okay, so for example, a very simple question. We have to find out the radius. The equation of radius is there. The speed is 70 miles per hour. The maximum rate of super elevation is 6%, and the coefficient of side friction is 0.1. Okay, what is the radius here? Tell me. How is it? Okay, now this value is what? Minimum or maximum? Is this minimum radius or maximum? This is minimum, okay? Somebody takes 2050, 2045, no problem, okay? You should not decrease it because then it will not be suitable for the speed you have. Clear? Any problem? Okay. Again, a very simple example. You have the radius. We have to find out the speed in this case. The radius is given. Okay, and that super elevation is also given. Okay.
How do we find F?
You have
Yeah, yeah. Now I'm just looking at what people were doing with the calculators. Yeah, half of them were already busy.
You guys know?
Huh? Yes, yes, yes. Okay. So just one point for the previous question as well as this one or any other. So I'm mentioning that the conversion factors are already part of the equation. Okay, so don't try to convert it yourself. That the time should be in this and the speed should be in this, and this already done. If you're using the equation with the factor there. Okay, so don't try to convert it yourself. And secondly, we need what here? What is the question saying? Give us what? Speed. Okay, and we have a factor here, side friction, which also depends upon speed. Okay, so either you know both of them or you don't know both of them. In the previous question, both of them were given. Okay, if I give one of them, then the other one is there. If I just tell you speed is this much, then F is no problem, right? There is F. Clear? Okay. So now we have two unknowns. In this case, speed and F both are unknowns. Okay. Either we produce another equation, okay, which obviously we cannot do, or we assume. We do trial and error with the assumption. Okay. So we have to assume some value of F here. Okay. And then we will see what is our answer. Then we check the answer. Okay. So which value you want to assume?
1.14.
1.4. 50.
Speed.
Now you already have the answer. Very good. Okay, what? 35? But for example, if I assume, let's say, for the sake of others, if I assume 0.1, what was my answer? So I'm finding out speed, right?
43.
Huh?
43.
43, okay? If F is 0.1, then speed should be 70. I got 43, that means my assumption is wrong, okay? Now, to correct the assumption, where should I go? I will look at my answer. The answer should have been 70. The one which I got is less than 70 or more than 70? It's less, so I have to go back in the speed table, okay? And then you can try different values, okay? So for example, if I try 0.13, what is my answer?
48.
Uh,
48.
48, okay? It should have been how much? 55, okay? So again I have to go back. Now how far can I go? Between 48 and 55 there is only one value possible, which is this value. Okay, so now I will assume this, which you already did, right? Okay, and you got the answer to be 48, right? Again? So again 48 or
48.99.
48.99. Okay. So now we look at, it's not exactly the value which we are looking for, right? Okay, it's not exactly the value I'm looking for. It should have been 50 exactly. It's not 50. Okay, but can I go further in any direction? No. If I go back, it will be 45, and I only tried the higher values. Okay, so I have to stop my calculation here. Okay, so my final F is 0.14 and the final speed is 48.9. Okay, if there was another value which I could have tried, I would have tried that value. Okay, if my answer was, for example, 43, then I could have tried 45 because there is still a value between my answer and the assumption. I could have tried this value. Okay, to know the exact value of F, now we say our speed is 48.99. Okay, now what is the value of F? Because this value of F is at 50. We can do interpolation, but if you look at the values of F, even if you do interpolation, we'll get what? 0.14, right? Because what's the difference between them? 0.01. Even if you do the interpolation, the difference between them will be 0.00 something, which is negligible. In the end, you will take 0.14, right? Okay, or if it was close to 45, then you would have taken 0.15, right? Okay, so in this case, there is no point of doing the interpolation. Clear? Okay, so you have to do trial and error here. You have to assume a value of f and see what the answer you are getting, and that answer should match with the value of speed from the table according to your assumption. Clear? Yes.
If you use this value, we'll get the radius at 793. It will be less than 800.
What?
The radius. If you use the 50.
If you use 50, okay.
Okay, we'll get the radius at 793.
No, speed is 48.99, done. We use speed 48.99. Just saying that somebody says no. Now tell me this, the f value at your speed. So you can do interpolation. Okay, but interpolation will still give you the same value. Right? The speed is done. I cannot now further make my calculation more accurate. Speed 48.99. I cannot go up and down in the table. Right? So speed is final. Clear? I was talking about the f value. Somebody says no, I need the f value for this speed which you have selected. So you have to take one of these values. Okay, clear? Any other question? Okay. Then we came to the other characteristic of the vehicle, which is the braking, the deceleration. Okay. So once the driver applies the brake, the distance covered during braking can be given as average speed into the time of braking. Okay, so if the driver pushed the brake for 2 seconds, okay, you want to find out how much distance he covered in these 2 seconds. So we will take the average of the speed of the 2 seconds, multiply by 2 seconds. Okay, it will give you the distance. Okay, now let's say when the driver pushed the brake, his aim was to stop. Okay, now if he is trying to stop, then his final speed is how much? 0. Okay, so I said we need average speed, right? So first speed plus 0 divided by 2. Okay. Okay, average speed. This was the initial speed. The final is 0. So s plus 0 divided by 2. Average speed. Got it? Okay. And then what's the other factor? Time. So speed upon deceleration gives you time. Clear? Okay. So then we merge these two values and we have this equation. Okay. And then we further simplify it. We make it 1.075. What did we do here? So there was 1 upon 2 here, right? 1 upon 2 is how much? 1.075? No. So what did we do? 1 upon 2 is how much? 0.5. Why didn't we add 0.5? What else did we do here? We had done it in the previous case as well. What did we do? The conversion. Okay. So again 0.5 multiplied by the conversion of the speed. And again it is square. Okay. So this is what we have done. Now we have deceleration here. Okay. So deceleration and skid resistance are related to each other. They are the factor which is called as skid resistance. Okay. So this is the resistance which is created between the tire and the pavement when you are doing what? Okay, braking, slowing down. Okay. So this factor is called as skid resistance, denoted with capital F. Okay. There was the F in the previous equation as well, right? What did we call it?
Side friction.
Side friction. That was small f, this is capital F. These are different, their values are different. Their methods are different. The methods to get them is different. Okay? Clear? Okay. So F equals to A upon G, where A is what?
Deceleration.
Deceleration. Okay. Now we have A here, right? So if F equals A upon G, then A equals what? G times F. So we will replace A with G into F. Clear? Okay. So I got this in the end. Now this equation, there are two things. One of them I assume to be 0. What did I assume 0 here?
Final.
Final speed. Okay, the final speed was assumed to be 0 because he said he's stopping, but maybe he's not stopping, just slowing down. Okay, so I have to make it general, I have to put the final speed. Okay, one thing. And second thing is what? The gradient. Okay, does the gradient have has an effect on the braking or not?
Yes.
It does, right? So it should be part of the equation. So this is the final equation after incorporating the gradient and the final speed. Okay, initial speed, final speed, and the effect of the gradient, and that is from there. So this will again give you, it will take the speed in miles per hour, give you the distance in feet. The speed in kilometers per hour, distance in meters. There, and the conversion factors are already there. Okay. Now, F was A upon G, right? Where G is this much. Okay. According to the research done by Ashto, the normal deceleration rate is equal to 11.2 feet per square seconds or 3.41 meter per square seconds. Okay. So if A is this much and G is this much, then what is F? How much is F? Capital F.
Depends on the road.
No, just do it. You have A and G, that's it. 0.347, okay. In what? Feet, right? In feet. What about meters? Why? Yes, you will tell me the right answer.
Same.
Why? What are you guys doing? How can it be same in feet and meter? Feet and meter are same? Huh? What happened? Somebody give me the right answer. You were doing something, right? Shah? No? Sorry? Because of the conversion. But you still did it, right? We see numbers and we want to do it, right? Very easy. This upon this, I can do it. Yes. Whether I have to or not, we have to do it. Okay? Yes. So, yes, so the G will be in meter per square second and A will be in meter per square second. So you are doing the conversion for both terms. So the answer will be the same. It's a ratio. Okay? And now you know it, right? And you will not forget, inshallah. The next time you take traffic, you will not do it, right? Okay. So when we say braking distance starts from here, right? When you push the brake. Okay? So then after you push the brake, your vehicle will cover some distance. Okay? So that is a braking distance, huh? After you push the brake. Okay? But before you push the brake, you have to decide I want to push it or not, right? So let's say there was a rock on the road, it fell from the moon. Okay? And you saw it, and then you push the brake. What do we call the time between these two things? Looking at the rock and pressing the brake. The perception reaction time. Okay? So that is before the braking. Perception reaction time is before the braking, and then we have the braking distance. Okay, so we have an accident investigator that has estimated the speed of a vehicle which has hit the abutment of the bridge, the wall of the bridge. Abutment meaning the wall of the bridge, the side wall of the bridge. Okay, and he or she estimated the speed to be 20 miles per hour based upon the damage of the car. So the mechanical engineers or the automotive engineers in the automotive industry, they have this relationship. They can look at the damage to the car and they can estimate the speed. Okay, now they posted as videos as well. You may have seen the car hitting the wall at 20 miles per hour, 30 miles per hour. Toyota hitting it and Ford hitting it, right? Okay.
Crash testing.
Sorry?
Crash testing.
Yeah, crash testing. Okay. So obviously they know the speed of the vehicle and they then see the damage. Okay. So they have these relationships. According to those relationships, the speed of the car was estimated to be 20 miles per hour. 20 miles per hour when? At the crash. Okay. The point where the crash happened, they saw some skid marks on the road. Okay, they saw some skid marks on the road. Skid marks are what marks?
Tire.
Huh?
Tire.
Tire, the marks made by the tire when you are doing what?
Brake.
Braking, right? And braking very hard. Okay, it makes a good sound as well, right? Mhm. So if you know the length of the skid marks, you know which distance? Braking distance. Okay, you know the braking distance. Okay, so they measured this distance and it was 175 feet. Okay, 175 feet. Why it is written as two different numbers? The total was 175 feet. Okay, but 100 feet was on the pavement. Okay, pavement is made up of asphalt, you know, right? Asphalt surface, and then, or the asphalt mixed design surface, and then we have the shoulder. Okay, shoulder could be made up of asphalt. In this case, it was not. How do I know? Because I have two factors of skid resistance, two different factors of skid resistance. Okay, if it was the same surface, the factors would have been the same. Okay, so these are showing that and it's written here as well, that the shoulder is of the grass type. Okay, so it is allowed to make shoulder of other surfaces, loose material, sand, aggregates, it's allowed. Okay, in this case, it's grass. Okay, there is no gradient involved, and we have to find out the speed of the vehicle at the beginning of the skid mark. So meaning what? When he was doing what? Brake. Okay, when he applied the brake, what was the initial speed at that moment? Okay, so when he pushed the brake, he covered then 100 feet on the pavement, right? After pushing the brake, he covered 100 feet on the pavement. And then he went from the pavement to the shoulder. Okay, do I know the speed? Do I know the initial speed when he applied the brake? No, I have to find out. Do I know the final speed when he went on to the shoulder?
Yes, zero.
Huh?
Zero.
No, this guy crashed. Okay, so there is no zero here. If it was zero, then everything is fine. Okay, so it was not zero, it was something else, we don't know. Okay, then he entered the shoulder. So I don't know the speed at which he entered the shoulder. From the shoulder he went to the abutment and he hit the abutment. Okay, so when the final speed on the shoulder was the speed at which he hit the abutment. What is that value? 20. Okay, so I know the final, right? I want the initial. Initial on what? Pavement or the shoulder? No, but I can get the initial for what right now? The shoulder. Okay, because I know the distance, I know the F value, and I know the final speed. So I can find out the initial speed for the shoulder. Okay, so give me the initial speed for the shoulder. How much is it? Okay, so this is the speed at which he entered the shoulder. When he entered the shoulder, he left what? The pavement. This is the final for the pavement. Okay, and the distance for the pavement was 100 feet. And the F value is 0.35. So how much is the initial speed on the pavement? Okay, correct? From today onwards, I will only ask people if it is correct or not who are not doing. Okay, but they are the bosses, right? They don't do. No? We approve. Okay. So you got what we did here, right? Okay. The final speed was given. The braking distance was given. Because of the different surfaces, the braking distance was divided into two parts. So that's why we have to do the question in two parts. First, for the shoulder, for which we knew the final speed, we found the initial, and then for the pavement, for which the initial of the shoulder became the final. Clear? Any questions? Okay. So we said what here, that to see something and then you stop. There are two parts in this whole process. Okay, from seeing to braking, what is this part? Perception reaction. Okay, and then from braking to stopping, the braking distance. Okay, so the total is called as total stopping distance. Okay, you need to see and decide and then you brake. Okay, so the total stopping distance has two parts: the braking distance and the perception reaction distance. The braking distance, we have this equation, and this is using the standard value of H2 for the deceleration rate. Okay, and this is the which part? Perception reaction. Okay, so this is perception reaction time multiplied by the speed. And what is this? No, the conversion factor. Okay, the one which I mentioned earlier. Okay, and this is if you are using it in meters, so only the conversion factor has changed. Clear? Okay, let's say our driver is traveling at a speed of 65 miles per hour. He's on a curve has level grade, so no gradient here, and he sees a truck overturned on the road at a distance of 350 feet. Okay, so when he sees the truck, the distance is 350 feet. The driver can, or he decelerated at a rate of 10 feet per square seconds. Okay, a lazy driver. The normal is 11.2. He is not normal. Okay, because he is not normal, we wish that he goes and hits the truck, which he did. Okay, you should get rid of these types of drivers, right? No? Okay, clear? So what are they asking for? They are asking for the final speed. Okay. Okay, what is the final speed for this driver? Huh? Check with each other. Okay. Easy, right? Okay. Now in this case, did you change the F value because the deceleration rate is different? Okay. We will not take 0.348. We'll take and the perception reaction time is the normal. There is a table which is given in the previous slides for the perception reaction time. The normal value of perception reaction time is 2.5 seconds. Okay, the normal value. Okay, and for the F value, this will not be 0.348. Sorry, I just copied the equation. The F value was A upon G, right? So it is how much? 0.31. Okay, this is with this value, right? Huh? 56.5. Okay. Clear? Huh? So instead of 0.348, you will use this one, okay? This is with the standard H2 deceleration. Clear? Okay. Now, why did the vehicle hit the truck? What is the reason?
He didn't brake enough.
Huh?
He didn't brake enough.
He didn't brake enough. You mean the deceleration rate was low? Okay, one reason. Anything else? Too fast. Okay,
Too fast on the curve.
too fast on a curve.
The distance when he do the brake was
Yes.
small.
Okay, the only engineer here. The others are murderers. Like the person died, and you are. He did this. He was too fast. He was too slow. What is this? Still blaming him. He died. Okay. He died. What else do you want? Should pray for him, right? No? Okay. So the distance. Okay, the distance at which he saw the truck. Okay, so that distance should have been enough for him to stop. Okay, and this is the distance we control, and we call it the stopping side distance or the side distance. Okay, the distance which the driver saw, the distance at which the driver saw the truck, that was his side distance. The 350 feet was his actual side distance. Okay, but in order to stop, he needed more. Okay, so this is part of the design of the highway, that any highway, any street, any intersection, whether it's a point or the whole segment, doesn't matter. Okay, you have to provide enough side distance for the driver. Okay, and the minimum is the side distance should be enough for doing what? Stopping. Okay, this is a minimum requirement. The side distance should be enough for stopping. Okay, so for example, if you are designing a road for a speed of 70 miles per hour, okay, then you have to make sure that on all parts of this highway, the driver has enough visibility, side distance to stop. Okay, so for example, if this is a case we have, then how much side distance we need in this case? The speed is 70 miles per hour and the time is 2.5 seconds, and obviously then we are not designing for a crash, right? We are designing for a stop. So the final speed would be 0. So how much will be the distance? Final speed would be 0.348 because it's a design problem. So we will just take the standard value. And 2.5 seconds is also standard.
726.6.
Okay, so all points on the highway should have a visibility of 726.6 feet. If it is not available, then the highway is not safe for the speed of 70 miles per hour. Clear? Okay. Yeah, this is another fun way of showing the side distance. This is from the Directorate of Traffic. Have you seen it? You didn't see it, right? So obviously they have not known you, right? Okay, but they tried to make you see it. They made a whole football field here. Okay, so even if you don't look at the distance, you look at the football field and you think that, yeah, they are doing some, football tournament or something. We'll go there and see it. Okay, anyway, so this is, if you are going at 100 kilometers per hour, then just for reaction you will need like around 20 meters, okay, which is almost 1/3 the football field. And if you're going at this speed and you try to stop, you will eventually go over the football field and into the audience, into the pavilion. Okay, you will kill some people and so on and so forth. Okay, so this is what they are trying to show you. They don't drive car on a football field. Okay. Yeah, we'll do it next time. Any questions?